You cannot be get it from in a scikit-learn. You directly use the function and call it for some of the parameters. You just directly calibrate the results. And you can also interpret by using the weight vector. That is also very helpful to fine tune that. And the space and time complexity is obviously big O of n into d, because we are just recomputing all the results with corresponding to the all the data points. And the space complexity we are going to be get as a big O of d. We are just calculating only for the prediction results, right? That is basic assumption to make anything. So let's go and implement. And the loss interpretation, this is very interesting when compared to geometrical interpretation. So what will happen with respect to the loss interpretation? We already seen something called as a sigmoid function, right? So this is just a logistic function. So whenever you have a loss, okay, varying loss between the 0, 1, obviously, the varying loss, you have all the negative results. You can see you will get all the negative results whenever you have loss one, and whenever you have, it will directly decreasing drastically without any interpretation or smoothing curve. And whenever you have a loss equal to 0, you will get all the positive results. This is the positive side and this is the negative side, right? So whenever you get all the results and the loss is equal to 0, you will get the positive results. Whenever you have a loss is equal to 1, you will get all the negative results. But what will happen if you apply the log with the squashing? This is the squashing with the log. Squashing, or you can also call it as a sigmoid term. So when you apply the squashing the sigmoid term with corresponding to the logistic curve, this is a logistic curve we had initially. That means the W transpose Xi. So whenever you apply that logistic curve, it will slightly decreasing. You can see slightly decreasing, not gradually decreasing, slightly decreasing whenever we have negative side of the results. And whenever you encounter the 0 term, here you can see whenever you encounter the 0 term, it's slightly decreasing again. It's not going down with corresponding to the loss value. It's slightly decreasing, and whenever we go somehow to reduce loss, so it's almost like greater than whatever we had, some logistic regression function. And something called as hinge loss also, when we are going to be used in the SPM model with respect to hinge loss, we are going to be calculate some of the loss with corresponding to the kernel. We can also get it from the SVM. We have two types of the SVM, soft SVM and also the hard margin SVM, and some other squared loss also. Okay, so these are losses. By using the losses, we are going to be get so many models. So by using the logistic loss, log loss, we are going to be get logistic regression. By using the hinge loss, we are going to be get SVM. By using the square loss, we are going to be get another model. So like that, we are going to be get all the models only for the loss interpretation. So this is also very interesting, I can say. Whenever you read, this is going to be very helpful to minimize our loss somehow. So let's go and implement the logistic regression. This is not our project. This is some sample notes to understand the logistic regression. How does that going to be helpful? You can also read some of the interview questions. How does that going to be helpful, and what are the different assumptions we have? Yeah, so these are the standard libraries which are going to be showcased in the logistic regression model. So this is a sample data set. I think this is the data set with regarding some passengers details and also whether a person is survived or not with corresponding details. Okay, so I think this is a Titanic data set maybe. Yeah, so we have some of the classes according to the travel details and also the fare and the age and the survived is the target here. So this is the target variable. These are all the independent variables. So let's also make some assumption to separate our dependent and the independent variables. So I'm just dropping the dependent variable survived one in the X data frame, and I'm just keeping aside with our target variable which survived in the Y data frame. The shape is very small. The data set is very small. You can also, and one more advantage for the logistic regression is whenever you have a large data set, it will work well better, because we are computing only for the distance of the data point side. If it is a tree based kind of the algorithm, it may not be satisfied with the large number of the data set. It completely fine tuned with respect to the time complexity. Because of the large number of the data set, it will compute the distance and calculate the results much faster when compared to the tree based mechanisms. Okay, so Obviously we are going to be get it from the scikit-learn, logistic regression, or any other models. Okay, so currently we are doing as a train and test bit. So this is also one very interesting splitting mechanisms. So what will happen if you split randomly? What will happen if you split time based split? So there are two mechanisms. One is a random splitting, and another one is a time based splitting. So if you split randomly, you will get eventually all the data points corresponding to the train set and all the data points corresponding to the test set. It will split in the ratio of 80%. Maybe it in the test set they're going to be taking consideration for the 20%. So what is the headache to learn for the trained data sets and the test data set? And one more thing, we can also get it from unseen data points, something called as a cross validation. So this is also very useful information to store somehow by using splitting of the concept. So you have a data set, but you have trained in your model. It will also identify some of the patterns, or it will identify some of the features to calculate the results at the end, whether you have to predict or whether you have to classify something. But how do you test it? How do you test it? That is the question, right? So if you have an unseen data points corresponding to whether a person is survived or not by using this example, maybe. So this is the training samples you have, but what will happen if I give unseen data points with you with your model? So how does that going to be helpful? In that case, we are going to be take train and test data sets. This is the test data set we are going to be get it from the train itself, and we can train by using, I can say, logistic model. We can train by using something called as a hyperparameter is lambda. We just now discussed with the regression term, right? So I will use train by using the model. I will use test data for the hyperparameter tuning, or the other metrics, what are other parameters what we had. But cross validation result, it is unseen data point. We haven't seen this data point yet in our training models. So somehow people will call it as for the training result to do model plus hyperparameter tuning, and somehow people will do training with model only and test with the lambda. That means hyperparameter tuning only. They will also calculate in the cross validation data set. This is unseen data set. Okay, so you already productionize this model. You want to know about how does a real-time world is going to be helpful this model. So how does unseen data point is going to be help us this model? So by using the class validation test results, you can say class validation accuracy results or test results is going to be help us to understand whenever you done the productionization of these models. So at that time you will be get conclusion. You will also make some of the BRD to your end users. That is make good assumption to get rate from your problem. So that is the reason we are just taking consideration for the train and test split. So here we are just taking consideration for the 80 and 20 split, and random set is nothing but we are just taking random data points. So yeah, so something called as the normalization and the standardization. So this is nothing but a rescaling of the data. I think we are going to be cover up this maybe in the next classes. The structure of this course itself is somehow you can say, firstly we have to cover up with all the Python skill set, then we can go into some of the EDA concepts, and then we go into some of the logistic regression and other models. But somehow the projects may not be matching with this curriculum. We had to change somehow. Okay, so let's focus on this notebook. We are doing something called as a normalization, right? So this is nothing but a rescaling of the data. Whenever you do you have all the features. Okay, so you have all the features with ranging different ranges. Let's take the future one, having height 100 and 300 and 400, and future 2 also with the same as like that, maybe the 0.9, 0.7 or 0.6. So what will happen if you directly train to the logistic regression? As we already learned something called as a weight vector is equal to 1, right? So whenever you cannot be do any kind of the rescaling of the data which ranges from 0 to 1, or which are having the standard deviation is equal to, and mean is equal to 0 and the standard deviation is equal to 1. That's how the techniques will work, standardization and the normalization. But I'm just explaining intuition way. How does that going to be helpful? If you cannot the rescaling of the data, it may not be give as a future interpretability. It may not be give as a future interpretability. That means we cannot be identify which feature having more interpretable when compared to that. And also it will going to be takes a lot of the time to run when compared to if you apply the direct feature transformation technique.